Hello everyone. In this video, I would like to talk a little bit about a very fundamental concept in understanding wireless channels, which is essentially this notion of multipath and which leads to the related topic of convolution. This is widely used in any channel estimation, all forms of localization, beamforming, in various aspects of communication and signal processing. So it's important to be able to have total clarity in this very core fundamental topic. Okay, let's get started. Imagine there is a transmitter and a receiver. And imagine the transmitter is sending a sequence of bits or characters such as A, B, C, D, and so forth. The question is, what is the receiver going to receive? If this was happening in deep space, let's say from the International Space Station to another orbiting satellite, then the signals would go from the transmitter to the receiver along a direct straight path, and the receiver would receive A, B, C, D, and so forth. But on Earth, in environments around us, things are not as simple. Why? Because in addition to this direct path, which is also called the line of sight path, LOS path, line of sight meaning it's the straight line path from the transmitter to the receiver. In addition to that, there are reflections that happen because of all kinds of surfaces in the environment. So there are ceilings, there are floors, there are chairs, there are tables, there are human bodies. All these surfaces are reflecting signals. And these signals could be wireless signals, the signals could be acoustic signals, the signals could be light signals. It applies to any of these wireless signals. So in this case, a signal from the transmitter might be reflecting off a surface and arriving at the receiver. There might be other surfaces from which they are reflecting and arriving at the receiver. So there are lots of surfaces around, and as a result, the receiver no longer gets something as simple as A, B, C, D, which is what the transmitter is transmitting. Our goal in this video is to understand, get some sense of what is it that the receiver will receive. And from that signal, how can the receiver decode or estimate what the transmitter was trying to send? Great. So to do this, let's consider the vertical direction as time. And let's say the transmitter is transmitting A, B, C, D, and the receiver is receiving the same characters. So the transmitter is sending A first, then B, then C, then D, and so forth. Obviously, it'll take some time for the signal to go from the transmitter to the receiver. So A will arrive at the receiver at this time, let's say. And then, because let's think of A having 1 unit of power. Let's say that's why we call it 1A, 1B, 1C, 1D. But because power would get dissipated in different directions while the signal is traveling, the receiver will receive only a part of the power. The rest of the power has dissipated in other directions. So let's call the receiver receiving, just for convenience's sake, 0.5A. Very good. Now, once B has been transmitted, B will again arrive at the receiver, and B will be 0.5 B this time, because the same amount of power will dissipate. But here is the interesting part. At this time, when B arrives, maybe the delayed signal A, which is this one, this blue signal, the one time reflected copy of the signal arrives from A, from the transmitter to A. Let's denote that with this blue line, blue dotted line. And because this signal, this blue dotted line signal reflected off from a surface, from this surface, it is obviously weaker than 0.5 A because it traveled longer and it got reflected by this surface. So this, at this time, second time instant, the receiver received 0.5 B plus maybe 0.3 A, which is a weaker A because of the reflection. Great. Now let's take C, which the transmitter transmits, and we'll see similar behavior. 0.5 C, because on that blue path, blue reflected path, now B will arrive over the blue reflected path. So we will have plus 0.3 B. But now maybe the even more delayed path, which is the, let's say, call it the green path. Now the green path arrives, which let's denote as the green dotted path that arrives from the transmitter to the receiver. Just to be clear, this delayed path is this delayed path. Okay. As a result, at time t3, let's call this the time t1. If this is time ti, this is time ti plus 1, this is time ti plus 2. Thus, at the third time instant, the receiver receives 0.5 C plus 0.3 B plus maybe 0.1 A. And let's say the room only gives you one line of sight path and two reflections. These reflections, by the way, are often called multipath, or in the case of acoustics, they're called echoes. So let's say the room gives you one line of sight and two multipath. Then when D comes from the transmitter to the receiver, what should you receive? You should receive 0.5 D plus 0.3 C plus 0.1 B. And you're not going to receive A anymore because the room around you does not have a third multipath that's coming in. You know, in reality, there are many more multipath reflections that happen in a room. But for our case, we'll just take this one, this simplified version, because it captures the main idea. Great. So now let's generalize this a little bit. Let's call the received signal H0A plus H1B plus H2C. This is the received signal at the third instant, right? Now, if the transmitter is sending, instead of ABC, x0, x1, so on till xn, then the received signal y0 is h0x0, y1 is h0x1 plus h1x0. Remember, just to be clear, h0 is zero point 0.5, h1 is 0.3, h2 is 0.1, right? So received signal, and remember x0 equals A, x1 equals B, x2 equals C, and so on. So y0 is 0.5 A. H0 is 0.5, x0 is A. Y1 is H0 is 0.5, x1 is B, H1 is 0.3, x0 is A, which is exactly what we had. Y1 matches this Y1. Great. Let's keep going. Y2, sorry, Y2 equals H0 x2 plus H1 x1 plus H2 x2. Y3 is H0 x3 plus H1 x2 plus H2 x1, so on. One way to visualize this is the following. Let's imagine that the channel is like a box which has H0, then H1 which is delayed, and H2 which is further delayed. And the input to the box is signal x0, x1, x2, and so on towards the left side. And the output of the channel is obviously y0, y1, y2, dot, dot, dot. So look, as the signal comes into the channel, the characters of the signal will get delayed by the channel. This is the channel that the room gives you. And this room is essentially multiplying each of the characters with different weights and delaying them based on those multipath propagation routes. So at the first instance, x0 interacts with h0 and y0 becomes x0 times h0, which is this. At the next instant, x1 gets transmitted, but look, while x1 is going the path, while x1 is going the h0 path, x0 is going the h1 path. Therefore, y1 becomes h0x1 plus h1x0. Finally, when the whole, or when the three characters of the signal are moving through the channel, let me move this properly. Then y2 becomes x or h0 x2 plus h1 x1 plus h2 x0. So this is exactly what is going on. We are looking at the same channel from different perspectives. One in this geometry perspective, one is this algebraic perspective, one is this kind of combination visual perspective where the signals are entering into the channel one character by character. Right? Now let's try to write the received signal y as a general equation. Let's say we want yn. Look, when it's y2, we want h to go from h0, h1 all the way till h2. So when it's yn, we want h to go from 0 to 1 all the way till n. Right? So then we can write yn is nothing but some sum where I goes from 0 to n, and h has to be indexed by I, because h should keep increasing. Now look at x. X goes the other way. Means in some sense you flipped x. In general, x is x0, x1, x2, but now you flipped x because you want the signal to come into the channel one at a time. So you flip x by writing that as x of minus I. But then as you shift one by one, you write that as n. So now let's test this out with y2. y2 equals I equals 0 to 2 hi times x of 2 minus I, which is when I is 0, you get h0 x of 2. When I is 1, or let's say plus, when I is 1, you get h1 x of 1, this was 2, plus when you get I as 2, you get h2 and you get x of 0. Okay? And that is exactly what this tells you. This is called convolution. So this equation over here is called convolution. In other words, the source signal that is coming from the transmitter gets convolved, means the channel mixes it up because of these delays and these attenuations, and gives the receiver a combination of these delayed copies of the signal. So then a natural question is, okay, how am I going to decipher what is x0, x1, x2? Because remember, this is what we are getting, and we need to figure out what ABC is. Right? In general, that's not easy. So what wireless radios and wireless technologies would do is the following. The transmitter would transmit a packet, and the packet would contain what is called a preamble. And this preamble essentially means there would be a bunch of bits that are globally known. That means the receiver would also know that when a packet is coming in, the first k bits are going to be exactly this, and they know the set of bits. Right? So let's call these bits 1, 1, 0, 0, 0, 1. Right? So the receiver knows that the first set of bits would be 1, 1, 0, 0, 0, 1. Okay? So now the receiver receives this packet, and let's call that signal y. So you can write that y n as hn convolved with xn. Hn convolved with xn would mean this, plus some noise, because when the receiver's hardware receives a noise, receives a signal. It obviously has noise in it because it cannot sample the signal exactly. There will be some random factor involved. The receiver gets yn and it must now decode x out of it. But once you know this preamble, you know what xn is because you know xn is 110001 only for the first part of the packet. So by using that part of the packet, the receiver decodes hn. And once it decodes hn, it hopes that the channel, that the reflections from the environment that I estimated during this part of the packet would hold true for the rest of the packet. And therefore, for the rest of the packet, it uses that estimated h to decode x. How does it do it? Well, this is where we go back to Fourier transform. We know that convolution in time domain, observe that this is time domain. This is time domain because n is time, essentially, a discrete form of time. So convolution in time is the same as multiplication in frequency, which means if you take the Fourier transform of that whole equation, then what you have is yf equals hf xf, this is a multiplication, plus nf, right? And then you can say that, oh, I can estimate hf by dividing yf by xf. And I know xf for the preamble part, plus minus nf by xf. We'll assume that this one is small, means xf is larger, stronger than nf, and therefore we'll get our estimate from hf, we'll get our estimate from xf from this term, from this term, from this term. And once we have that hf, we will convert it back by using an IFFT of hf. We'll get hn. And then we will plug that hn back into yn equals hn convolved with xn plus n. We'll plug this, we will plug this hn back here for non-preamble bits. So once we know yn and hn, then we can figure out xn from there. That's how we decode bits from a multipath signal. Okay, I hope this gives you a sense of how wireless channels work. And in many, many applications, you'll realize that all kinds of problems come up. In some cases, let's say a human is speaking and a voice assistant is receiving a signal. The voice assistant has no preamble in that case because human beings are not sending any globally known speech signal, right, as a preamble. So in that case, it's difficult to estimate this channel H. If you want to do localization, you want to pull out this H because this H is going to give you what the room structure looks like and where you are likely to be. If you want to decode a signal, you want to pull out this X. There are many, many applications around this. Okay, great. We'll stop here and thank you for watching.